Thank you. You haven't seen the talk, so don't clap yet. All right. Hi, everyone. I'm Arthur Breitman. I'm a co-founder of Tezos, and I don't know the crowd, so I wasn't sure what I would talk about. And then I decided that we're going to be a bit technical, but it will be technical but high level. And I want to explain how blockchains can scale, because I think there's a myth, the myth that blockchain don't scale. And that myth came from the fact that, well, for a long time they didn't, and people didn't really have any good ideas on how to make them scale. And I think that's changed. So I'll describe what we do. And first, what is scaling? And scaling is not a magnitude. Scaling doesn't mean you go from doing, 1x to 100x or 1000x. Ideally, scaling is a functional dependency, right? It says, like, look, if you add more resources to the system, do you get more output? Right, that's scaling. A simple example of scaling is fire stations. If I am in a city and I double the numbers of fire stations, a priori, I double the amount of fires I can extinguish in a city. See, that's very simple. That's scaling. And in fact, most things that we're used to scale. If we have a conference room that's twice as big, we can have twice as many people. There's limits, of course, to scaling. You could imagine a city where you have so many fire stations and so many fire trucks that you only have traffic jams, right? So then you stop scaling, which is why some of these curves here, like they bend down after some point. But in general, like there's going to be a regime between like certain parameters, maybe between 1x and 1,000,000x, where you say, okay, in that regime, roughly I have a scaling curve. And by and large, blockchains don't do that. You can add many more computers to a blockchain. You're going to get more decentralization, but you're not going to get more throughput, you're not going to get more transaction, you're not going to get any of that. You just get more computers all doing the same work, all doing the same validation, which is annoying. You would like your network to be able to be elastic, like the more demand you have for transactions, the more you can process. So can we do that? And in order to do that, let's look at what it is that block validators and those block producers, they're called miners in Bitcoin, block producers in other chains, because no one really mines anymore outside of Bitcoin. So what do they do, those validators? Well, the first thing they do is they select which transactions to include in blocks, right? They go on the peer-to-peer network, and then they select all these transactions one by one, and they say, okay, this is my block. I'm going to put all of these transactions in my block. The second thing is that they also order the transaction. So they run a consensus algorithm with each other to know which blocks belong to the chain, which don't belong to the chain. And in ordering the blocks and in ordering the transaction within the blocks, they create an ordering. And the ordering part sounds boring, right? You're just saying like, oh, which transaction came first, this one or that one. That doesn't sound very important. What sounds really important is maybe computing the transactions, but it's actually the hardest part in all of this, right? That's the part that requires decentralization. That's the part that's required messy crypto economics and tokens and all of that. It's a consensus because ultimately ordering is what solves the double spending problem. You solve the double spending problem. If I try to spend my money with one merchant and another merchant, the way you can disambiguate which spend is correct and which one is not is by knowing which one came first. They also compute and maintain the state of the ledger. So they take all these transactions and then they see what is the effect of the transaction. So they run a lot of compute. And it sounds like this would be really the nerve of all the work that's happening. But it turns out that's the easiest part to deal with. And then they make the transaction data available to other parties, which sounds very weird when you... Data availability is not something that's very intuitive, and it's something that took me a lot of time to understand. But it's also key to the double spending problem. If I make two transactions at two different places, well, the order matters, but the other place also needs to know that I don't have a conflicting transaction, so they need to know what the data is. The way that Bitcoin solved the double spending problem is by deciding to put all the transactions into one public journal that everyone can read. So none of them sounds very good for scaling. If you have to put all the data in one place where everyone is going to read it and everyone is going to compute everything, you don't really scale. So the way we can do this is by scaling by unbundling, right? We're going to take those different validator functions and we're going to try to not have them be done by the validators ideally. So instead of proposing transactions to the network, we could propose entire blocks so that at least if I'm a validator, I don't have to select transactions I can be given blocks, and maybe I choose this block because it pays me this much. I choose this block because it pays me that much. So that's a sometimes called, in Ethereum world, they call it the proposer-builder separation. Consensus nodes agree on blocks. That, I think we don't have a way to escape that. Your consensus nodes still need to agree on ordering of block. But fortunately, so long as that's all they have to do, and so long as we can cram a lot of transactions and compute in these blocks, that shouldn't be a problem. We want to outsource execution, potentially shard it, and by that I mean have multiple people contribute to the same computation. Data availability, we can try to outsource it, or we can try to shard it. And then what about state? All right, so what can we do? All right, so let's talk about execution, because execution feels like the hard part, right? You're computing all this transaction. That sounds intensive. So sharding execution is appealing because you would scale the compute ability of the whole network, right? You have all these computers in the network you want to scale, so why not have everyone contribute a little bit of compute power to do this one big computation? That doesn't really work. You know, in general, running parallel algorithms is very tricky. And if you do it with latency across an entire network, that's not going to work very well. So in practice, any reasonable attempt at sharding execution will align with partitions of the state. And what that means is you have a ledger, and you're going to say, okay, this is zone A of the ledger. Maybe you say like, okay, everyone who is in Europe, you're going to use zone A. And then you have zone B of the ledger, and you say, okay, everyone who's in Americas, use zone B. And then you can process this transaction in parallel so long as you have a transaction that goes between, you know, someone from zone A to someone from zone A. You process that in parallel to transactions which are happening from zone B to zone B. And then somehow you find a way to do cross-zone transactions at some other point. That can work, but you lose a little bit of connectivity when you do that. But also what's more important is that the validators of the chain, they need to find a scalable way to trust outsourced execution, right? If I ask someone else to compute all of this, how do I know that it's valid? And so enter rollups. Rollups have been very popular, and if you read about rollups on the internet, you will read that they speed up computation by compressing all the transactions and rolling them up, and that's wrong. That's what people thought when they were building rollups, and they were building something interesting, but now that we understand them better, that's not really what matters. So the idea of a rollup is you're going to take some transactions and you're going to post them on the chain just like regular transactions, but instead of targeting the chain, they're going to just target a rollup. And the validators are not going to bother executing them. That's not their problem. They're making them available, they're putting them on a chain. Yep, this transaction is here. What does it do? Not our problem. That logic is going to be handled by the rollup validators, which are running separate nodes. And so the rollup validators, what they'll do is they can post cryptographic commitments to the state of the rollup on the main chain. And what that lets you do is that once you have these commitments on the main chain, then you can do cross-rollup messages, right? You can say, well, I know that this rollup is in that state, and I know that this rollup is in that state, and now I can synchronize the two of them. So it gives you this kind of parallel execution and horizontal scaling, right? You process things in parallel by zones. And also, you know, the nice thing is that they maintain their own state, so you don't have to worry about that. Every rollup node maintains the state. The one big problem you have is that for all you know, how do you know that the rollup commitments are correct? You know, the way you know things are correct on a regular blockchain is you execute everything. Now that with outsourced execution, how do we know that it's valid? And so one idea is you include an execution trace of a program. So what's an execution trace? Well, when you take a program on a computer, it always gets executed step by step, right? You have a set of assembly instructions, and you're going to say, read a little bit of memory here, put a bit of memory here, now add these 2 bits of memory, one by one by one by one. So one thing you could do is you could do a journal of all these computations, everything that's happened in the memory. You roll that out, that gives you a trace. So we could put traces, and then we could say, okay, I'm a validator. I'm going to just like look at different pieces of that trace and see if it's correct, see if every little step is correct. You break it down in small steps, which are easy to verify. Now, the problem with this approach is that most validators are only, are going to miss it if there's a single invalid transition, right? A single invalid transition, some of them are going to see it, but most people are going to miss it if you're only looking at a small subset of those steps. And a single invalid step, of course, in a trace could change everything, right? You could set an account to 0, or you could set it to 10,000. That takes one step. So in one step, you could have a completely bogus execution. So a better idea is that you take your trace and then you turn it into a hologram. And it sounds like I'm making this up, but it's true. A hologram. So, if you have a physical hologram and you break it into 2 pieces, each piece actually has a little bit of hologram. And the way it works, if you study optics, is like a hologram is actually a Fourier transform of an image in aperture. And so this is a metaphor, but it's actually a fairly deep metaphor. If you do a Fourier transform of your trace and use error correcting codes, you find something that has a property of a hologram, which is like if you verify small pieces, you can get very strong guarantees about the entire thing. That's the magic of cryptography, and that's a technique you see in zero-knowledge proofs. So the problem with holograms is that first they require a computing model that's very different from computer hardware. If I give you the execution trace of some regular program on some Intel CPU, you are not going to be able to turn it into a hologram, right? So you need to do terrible mathematical things to that trace before it actually is willing to bend itself to your desire to be a hologram. You can do it. You have to use computational model such as arithmetic circuits in finite fields, or you have to use algebraic rules in finite fields. So there's like models of computation, and we'll let you do this, but most of them do not. And when you compute things in those models, you are going to be slower by several orders of magnitude. So those are essentially this approach that I've described here. They're called either ZK rollups or validated rollups. It's a fantastic idea. I wrote about them in 2017 when I was criticizing the Ethereum sharding approach. They're a great idea, really beautiful science, not very practical when you look at the amount of compute it actually takes. A second idea would be to use trusted execution environment. So a trusted execution environment is essentially hardware. You have a CPU, and then there's a feature in the CPU that says, okay, we're going to make it so that the CPU is going to monitor the execution and is going to use a private key that's inside each CPU to sign the results. It's like the CPU is telling you like, yeah, I'm a CPU and I monitor what happened and I tell you like this is legitimate. It's a great idea. It exists in Intel as a form of SGX. There's also versions for Android and for AMD. And the problem is they've all been, well, maybe not all, but the most popular one, SGX, has been broken repeatedly. It just keeps being broken. And a lot of it is by side channel attacks. So in theory, you can't know what happens in the CPU, but then if you measure its power, you look, like a little bit at what the pins are doing, you can infer what's going on, and you can get the keys. And the other problem is that you still have to trust Intel, because at the end of the day, someone put a private key in there, and so someone has the power to actually forge a lot of these certificates. So it's a neat idea, but I don't think you should depend on it for things which are very security critical. Because again, it keeps being broken, and at this point it's getting ridiculous. So the third idea we have here, oops, no, optimistic rollups. So also a popular term. So, no, that's not it. There we go, optimistic rollup, that's an optimistic computer right there. What they will do is instead of having a cryptographic proof or a hardware proof that the commitment is correct, you essentially are going to let rollup validators post whatever they want, but if they post something fake, you will let them be challenged. And so if you have one honest validator in your rollup node, they will see that other rollups are trying to cheat. They do the computation and then they give the wrong results to the main chain. So someone can come in and say, wait a second, that result is false. And then you have a game that plays on the chain. It's a dispute. And using binary splitting on the execution trace, you can find the first point of execution where you think there's a disagreement to replay that on the chain. And so in this model, your main chain acts like a judge. Essentially, it sees a conflict, says, well, someone tells me this is the result of the computation, someone else tells me the result is different, let's find out what happened. It's a beautiful model, and it has benefits and drawbacks. So the main benefit is that there's zero overhead in computing. You can compute as fast as you want. You can run your optimistic rollup on a super fast machine with lots of CPUs, lots of RAM, whatever you want. It runs in any computational model you want. You're not dependent on an embedding into some mathematical language. And that's very powerful because, zero overhead. Drawbacks. They are complex to implement. They have many moving parts. And on the one hand, you might think that, well, I understand this. You're playing a game, someone says this, someone says that. It's very understandable on an elementary level. It's certainly a lot easier to understand that the advanced mathematics it takes to do zero-knowledge proofs. But the thing with zero-knowledge proofs is that once you've implemented your prover and your verifier, and once you're very confident in your verifier, in some sense, the surface for bug is small, right? You have this very complex, very intricate piece of mathematics, but if you're very, very confident it works, it's a small surface where you could get it wrong. With optimistic rollups, there's many moving parts. There are games, there are a lot of things happening, and so the implementation is actually more complex. And there's also a stronger assumption. Instead of having no honest participants, cryptography proves everything, now you have to assume that you have a single honest person. So if you find one honest rollup participant, the rollup is going to be protected. My contention here is that if your rollup does anything of worse, then surely there's going to be at least one honest person who cares about it. If you have no honest person who cares enough about your rollup to run a node, then it will not be secure. And also it assumes that there's no censorship at the base layer. Because it relies on disputes, you're dependent on your validators to essentially be willing to include those disputes, because otherwise they could pretend everything is fine. You can somewhat trade off this risk of censorship with latency by allowing the participant of the chain to detect censorship and potentially hard fork if there's censorship. So trade-offs. Essentially, you have something that really gives you much, much better computation, but is a bit more complex and clunky. So horizontal or vertical scaling. So horizontal scaling is when you do many things in parallel. You have, let's say, many firehouses in a city. Vertical scaling is when you have one big giant firehouse with a huge truck, and your truck has way more water pressure and can reach buildings very, very far. So rollups will let you do horizontal scaling because you can run many rollups in parallel. Main chain doesn't care, and they can pass messages to each other. But the synchronization between the state is cumbersome. It's kind of like you're communicating through a small pipe. And in the case of optimistic rollups, it can be very slow because you want time for the main chain to be able to process disputes, and as a result, before one rollup can be convinced of the state of another rollup, it could take days or weeks depending on how conservative you want to be with security. But the nice thing is you can also do vertical scaling, and you've probably heard a debate in the blockchain world about whether or not your blockchain should do horizontal scaling with L2 or vertical scaling. And if you hear the proponents of horizontal scaling, they will say, well, you can't do vertical scaling because we want to be decentralized, we want people to be able to run these very light clients, and so let's just have all of these layer 2 solutions, and then people will use those. Yes, it's a bit more cumbersome because they need to talk to each other, but it's worth it for decentralization. Now, if you hear proponent of vertical scaling, they will say, oh, who cares? Let's let everyone have a very large computer. If you take part in a proof of stake network, at the end of the day, your stake is probably worth a lot more than your computer. Compute is not that expensive. People can have very, very large computers. And in practice, that's not really scaling, right? It's just increasing the order of magnitude. But if you increase it enough, maybe that's all you need. And the nice thing with rollups is that they do both. They do vertical scaling. Why? Because if you run a single rollup with a very beefy computer, very, very expensive, you don't have any decentralization issue. You see, the reason you need decentralization in a blockchain is for consensus. Why? Because you're relying on the hopes that you're going to have an honest majority. And for that, you want as many people participating in your blockchain as possible, as many validators all around the world to ensure that it's easy for people to participate. But if you have this very, very large compute demands, that's not necessarily possible. Now, with a rollup, you don't have an honest majority assumption. You only have a single party. So if you're telling me hey, it takes a huge computer to run the validators on your blockchain, and a majority of people need to have this huge computer, that's tough. If you're telling me oh, look, all you need is one honest person with a big computer, that's great. So you can have the best of both worlds. You can do vertical scaling with rollups, And that's way better than doing vertical scaling on your base layer. Data availability, that's a strange concept. I'm going to speed up a little bit because I'm running low on time. But the idea is that network participants must know what transactions happen to compute things. For validity rollup, if you don't have the data, then the chain kind of stops because you can't really process any more transactions because you don't know the state. That can lead to ransoms. People could say like, look, I'll withhold the data and your funds will be locked until I give you the data. For optimistic rollup, failure in data availability are a bit worse. It can lead to safety faults. So the standard model is that the validators who look at the chain only accept it if they can download everything. If all the transactions are on a chain and everyone sees everything, they'll accept it. That works, but it doesn't scale because everyone has to download everything. It would be nice if the amount of downloads scaled with the number of nodes. And you can do that by sharding data. So here's the idea. Instead of everyone downloading everything, we'll have everyone download a small subset of the data. Problem, if there's small pieces missing, a lot of people are not going to notice. Better idea, you turn your data into a hologram. Again, so it's the same idea for compute, but it works a lot better when you do it for data. So you applied cryptographically verified error correcting code to your data. Every validator samples parts of the data, and the magic is that with very high probability, a very high fraction of validators will notice if any part of the data is missing. And if the data is not available, no big deal. You just consider that there are no blocks. So what's important is that approach does not depend on block producers being honest. It's really anyone who's just observing the network can figure this out for themselves. And if they finalize a block which doesn't have available data, then it doesn't matter, you just ignore the block. That's liveness, they can cause liveness faults, but we already know that. Putting it all together, so what does Tezos offer? Because this is essentially all what's implemented or being implemented in Tezos. We have enshrined optimistic rollups. They shipped a few months ago. So you can run any chain you want on Tezos, including Ethereum, any type of transaction logic you want, as long as you can compile it to WASM, WebAssembly. That includes Go, that includes soon Python, assembly scripts. So there's a lot of language, Rust, a lot of languages compiled to WASM. You compile any program you want, you can run it as a rollup on Tezos, and all of the logic is handled at the protocol level. It's completely free to use. There's no weird license. No commercial deed is needed. We are not going to take your firstborn or a portion of your revenue. It's completely free to enter. And it's available since our Mumbai upgrade. Data availability, sharding, and sampling is still at the prototype level. But we should have the first version is on several dev team roadmap for this year. And UHT, which is a vertically scaling rollup that we're building, it's built for interoperability, developer experience, performance, and that's coming later in 2024. All right, thank you all for listening. I believe that Tezos was at the forefront of proof of stake, being the first major proof of stake to launch, and is now at the forefront of scaling by truly bringing scalability. We've seen a lot of hype around small use cases in the blockchain space over the past few years. I believe one ingredient that's been missing for mass adoption has been the ability to have truly large scale in terms of what's being processed. And that's going to be offered for the first time on a Tezos chain. Thanks all for listening. Okay, any question about scaling Tezos or anything really? Yes. Yeah. Can you speak up?
To say that like allow the validator with high probability would catch something in the
Yeah, so the way the data sampling works is the following. So the first thing is use an error correcting code. Let's say you use an error correcting code with a rate of 2. So essentially you double the size of your data, but you're making the assumption that so long as you have half of, more than 51% of the data, then you can get everything. That's what makes the magic happens. So the way sampling works is like, if I'm a node on a network, I see a new block and I say, that's interesting. I'm going to sample some of that data. And maybe I sample 64 little pieces of that data randomly. Now, if all of the data is available, if more than 51% of the data is available, if less than 50% of the data is available, it's very unlikely that I'm going to be able to get all those shards, right? If less than 50% is available, there's only a 1 in 2 chance that I can collect each little piece. And as a result, with like, if I try to collect 64 pieces, very high probability I'm going to notice if it's not available. Now, there are tricks people could play. If I am a known entity, someone who's malicious could say like, could just feed me this information and say like, you in particular, I'm only going to give you the information. I'm going to make you believe that you have this data. However, if you have a large number of nodes, and I'm not talking about block producers, just people who are just running the software, and in general, you probably have a good order of, or 2 of magnitude of people who run nodes as opposed to people who are producing blocks. So long as you have enough of those, you can convince a few people that this is happening, although it's tough, like it requires a level of control of the network that's actually in practice quite difficult to obtain. You need to know that the person is not running another node somewhere, so it would be hard to pull off. And in practice, that's why I also said with high probability, most of the nodes are going to, and not none of the nodes. So, you know, you might trick a few, but 99% of the nodes are going to notice. And then if your node gets tricked, pretty sure you're going to talk to other people and figure out that, oh, actually the chain is stopped, something went wrong, I should, maybe I should sample more. But yes, there are little subtleties here. Yes?
Thank you for the talk. How do you compare your consensus with something like Tendermint in like terms of scaling, etc.?
Sure. So our consensus is actually very close to Tendermint. We call it Tenderbake. It's essentially Tendermint based, but instead of having the whole set of validators participate, we have a random subset of validators being selected, and that random subset participates in the chain. But otherwise, very similar to Tendermint. For a while, I think it was thought that there was this deep connection between scaling and the consensus algorithm, and I think we're kind of moving away from that. I would say that the consensus algorithm is most relevant for latency, right? And the thing that you get from having finality, a lot of time people will think, oh, I have finality, therefore I am more guaranteed about the security of the chain, but that's not really it. Because if you have probabilistic finality and you say, okay, with probability 99.9999%, I have finality, that's good enough. What the finality gives you is actually semi-synchronous safety on a network. It means essentially that you're not going to get tricked just because the network is slow. And that's one of the problems that traditional consensus algorithms like Nakamoto consensus in Bitcoin have, is that if the networks get very, very slow, the security goes down. Whereas with algorithms like Tendermint, for example, or Tenderbeck in Tezos, as the network gets slow, your chain just gets slower. But essentially it speeds adapt to the speeds of the network. And because of that, you don't have to be conservative, right? Bitcoin makes this very conservative assumption of 10 minutes per block because it says like, well, I don't know how good the network is. For all I know, it's going to take more than 10 minutes for my block to propagate. So they have to be conservative. Whereas, you know, if you have finality, you could say like, look, I'm going to assume it's 1 second between block. And if I'm wrong, it's all right. You know, the chain will be slower. So it's, that's the main benefit is latency, not so much scaling.
I'm not sure if you have looked at ABCI++, but I think ABCI++ solves most of these issues that you're like describing. So like, but it's up to you. Like, have you seen ABCI++?
I have not seen the ABCI++, so I can't really speak to that.
Okay, we can take one last question. I guess.
Hi, what do you think is what would lead to the adoption of Tezos? What is slowing down Tezos adoption now, and what will eventually help the adoption?
Actually, Tezos has fairly decent adoption. I would say what's slowing down adoption the most is probably perception. I would say there's a wide gap in perception between what Tezos is and what a lot of people perceive Tezos to be. So I would say there's many people entered the industry around 2021, and if you ask them about Tezos, they will say, what's Tezos? And other people will say like, oh yeah, Tezos. That's still a thing. But actually the chain has gone through 14 upgrades, so it started a while ago, but it's probably one of, I would say 3 or 4 of the most technologically advanced chain today that are available. It has pretty decent adoption, very strong art community, a lot of interesting corporate use cases, specifically in Europe and in France in particular. But the difference in perception is probably making it difficult today to get more adoption. So I would say that's probably the main bottleneck.